let's do an example where we have to find a formula for dy dx. So if x squared plus y squared equals 4x minus 7y plus 15, find a formula for dy dx. So here we have an implicitly defined y. We cannot find a formula for y, one that describes y as a function of x. So, to find dy dx, we need to differentiate both sides with respect to x. So, as we do this, the left-hand side, the fundamental operation is addition. So, we can say the derivative of the sum is the sum of the derivatives, and likewise on the right-hand side. So we can take the derivatives with respect to x of each term separately. So let's start with the first one on the left-hand side. The derivative of x squared with respect to x is 2x. Now we want to find the derivative of y squared with respect to x. So y depends on x, so we have to use a chain rule to compute this derivative. To compute the derivative, we need to compute the derivative with respect to y of y squared times the derivative of y with respect to x. That's our chain rule. Moving further to the right, the derivative of 4x with respect to x is 4. And then likewise, when we take the derivative of negative 7y with respect to x, we first have to take the derivative with respect to y and then multiply by the derivative of y with respect to x. And then the derivative of 15 with respect to x is 0. So I'm just going to go ahead and rewrite this at the top of the next page. Oh, that's not what I meant to do. There we go. And I just left off that plus 0 on the side. So now what we need to do is take the derivative of y squared with respect to y, leaving everything else the same. We get 2x plus 2y dy dx. And then we also have to take the derivative of negative 7y with respect to y. So I get 4 plus negative 7 dy dx. So what we're supposed to be doing is find a formula for dy dx. So we need to solve for dy dx, and we see dy dx appearing in two places. So think of dy dx like a variable here. I've got an equation with lots of variables in it, and I need to solve for a very particular one. So I'm going to move all the dy dx terms to one side and move all the other terms to the other. So we have 2y dy dx plus 7 dy dx equals 4 minus 2x. And now again, we've got dy dx appearing in two places. We want there only to be one dy dx, so we're going to factor it out and get 2y plus 7 times dy dx equals 4 minus 2x. And then dividing both sides by 2y plus 7, we get dy dx equals 4 minus 2x over 2y plus 7. And there's our formula. I know there is a y in the formula for dy dx, but remember this was an implicitly defined function to begin with. We implicitly defined y, and so it makes sense there would be a y in our answer. So let's ask a couple more questions. Under what conditions on x and y is the tangent line to this curve horizontal or vertical? Okay, so we have a formula for dy dx. Remember, dy dx is going to give us the slope of the tangent line. When, there's our formula, and when the tangent line is horizontal, our slope is 0. So we could solve this. This tells us that 4 minus 2x equals 0. And so 4 equals 2x, and x equals 2. When x equals 2, we could go ahead and figure out what y is by looking at our original equation. Here's our original equation to figure out what y is when x is 2. we fill in 2 for x. So 4 plus y squared equals 8 minus 7y plus 15. Or in other words, y squared plus 7y minus 19 equals 0. So here are our requirements on x and y when the tangent line is horizontal. So let's see what that looks like on the actual graph. So here's our graph of x squared plus y squared equals 4x minus 7y plus 15. It might have surprised you that this is the graph of a circle. We see that when x is 2, we're right here at the top or the bottom of the circle, and those are exactly when the tangent line is horizontal. So it might make sense that the tangent line is vertical at the left and right ends of the circle. So let's see if we can algebraically construct this. So we want to know when the tangent line is vertical. That means that the slope is undefined. So we get dy dx equals 4 minus 2x over 2y plus 7. So we're going to get a vertical tangent line whenever this denominator is 0 and the numerator is not 0. Remember, if we were to get 0 over 0, that would be an indeterminate form, and that means that we might have had a hole or something else. So 2y plus 7 equals 0, means 2y equals negative 7, or y equals negative 7 over 2. Okay, so if y equals negative 7 over 2, we go back to our original function, which tells us we have x squared plus y squared equals 4x minus 7y plus 15. So when y equals negative 7 over 2, we get x squared plus negative 7 halves squared, which equals 4x minus 7 times negative 7 halves plus 15. Okay, and this gives us a requirement on x that tells us that x squared minus 4x, and let's see if we can do this, 49 fourths minus 49 halves, that's negative 49 fourths, plus 15 gives us negative 19 halves. That is going to equal 0, and that's going to give us 2 x values. Okay, and if we go back and look at our graph, we have this place right here, this place right here, and this place right here. Those are when y, that's when y equals negative 3 halves, and that gives us that x value and that x value. Okay. All right, so look forward to a lot more implicit differentiation in class.